Hi everybody, thanks for the opportunity to talk with you today. So I'm going to start with the last part of this long and possibly intimidating title first, which is the probabilistic seismic hazard model part. So what do we mean by that? Well, what we're interested in doing is we're interested in answering the question, what will peak earthquake shaking be at a certain location or over a certain region over, say, the next 50 years? And obviously, having this information is useful for a lot of different applications, right? For doing things like building buildings and figuring out how strong they need to be, planning for earthquakes, emergency planning and disasters, and for insurance agencies to set insurance rates. And so the way that this is done, the way that we do probabilistic seismic hazard analysis, or PSHA, is actually pretty straightforward. We start with a list of earthquakes. We say, okay, what are all the possible large earthquakes that might occur that might affect your location of interest? Say, for example, downtown Los Angeles. Then we take those earthquakes, and for each one we have to figure out, well, how much shaking will it cause? Right, and then we take these shaking levels, we combine them with the likelihood that each earthquake occurs, and then you end up with what's called a hazard curve, like the one you see here in red. It's pretty simple. On the x-axis, we have the amount of shaking in terms of g. On the y-axis, you have the likelihood of exceeding that amount of shaking. And so, of course, you have a high probability of having a little bit of shaking down to a low probability of having a lot of shaking. If you're interested in building a building, for example, you'd go out to the 2% and 50-year level, which is a typical level that's used. You'd go down here and you'd see, okay, my building needs to withstand 0.4 Gs of acceleration. This is a real hazard curve for downtown Los Angeles. If you want to understand the hazard for a whole region, you can then repeat this process over and over for different locations, and then you can interpolate the results onto a hazard map. And in doing so, you can understand, for example here, the hazard for all of Southern California. And so this is one of the big projects that we do at the Southern California Earthquake Center at SCEC. In particular, we use what we call the CyberShake platform to simulate over 500,000 different earthquakes to produce our PSHA results. One of the things that's important to us, of course, as we go through is to continue to improve our estimates, right? As we saw, these estimates are used by a lot of decision makers, and so the better results we can produce, then the more useful it is to society. And so how do we do that? Well, in order to do that, we have to go through and improve the individual steps in this process. And so that's what I'm going to talk about today, is how we've been working on Blue Waters to improve these elements of PSHA and how they enable us to produce better results. So the first element is that list of earthquakes, right? We call this an earthquake rupture forecast. And so it tells us, okay, here's how big potential earthquakes might be. Here's the faults they might occur on. And here's the probabilities for them. Here's how often they occur. And so how do you produce a list like this? How do you produce an ERF? Well, typically you produce this empirically. So you go out and you gather historic data. You take a look at recurrence intervals. How often do earthquakes occur on certain faults? You look at slip and stress rates, right? If a fault accumulates stress at the rate of 1 centimeter per year, then it's got to slip enough to make up for that over a long time frame. And so you can kind of put this all together and you can generate an ERF. There's a graphical representation of one here on the right. So you see the different faults lit up. The colors correspond to the probability of experiencing a major earthquake. Typically, you actually end up generating an entire logic tree because there are a lot of assumptions that are built in and different reasonable people disagree about those assumptions. But one of the things that can be difficult then is going from this extensive logic tree to something that you can then generate a small enough list that you can simulate. You may remember I said that currently we're simulating about 500,000 events for each location of interest. But this model that I'm showing here, which is the most recent ERF for California, we'd have to simulate something like 25 million events in order to capture sufficient variability. And even on a machine like Blue Waters, that isn't really computationally tractable. So we've been saying, okay, is there another approach where we can get a improved earthquake rupture forecast that doesn't require simulating 25 million events? And it turns out that there is. This is something we're particularly excited about. What we're actually doing here is we're using, rather than an empirical approach, a physics-based approach to simulate an earthquake rupture forecast. It's a code called RSQSim, and what essentially it does is it simulates the entire California fault system. So you load it up and you let it go and you simulate hundreds of thousands or millions of years of time, and what you end up with then is a very long simulated earthquake catalog. The movie down here is just kind of showing you a representation of that. Every time something lights up, that's an earthquake that's occurred somewhere. And so you can see, right, certain segments go off more often than others, but things are occurring throughout the fault system. And this enables us to get useful information that we can't get any other way, right? We don't have 1 million years of earthquake history in California, right? Paleoseismic data just doesn't go back that far. But by doing this, we're able to get out, look at cycles, look at correlations between certain faults, and get out other kinds of information that we just can't get at any other way. This particular code is a CPU code. It's spatially decomposed based on the fault surfaces. The challenge in terms of scalability with it is that you have to have global communication because you have to figure out, okay, which event in the entire fault system ruptures first, and then fire that one off, and then that propagates slip and stress changes throughout the rest of the system. Typically speaking, it takes about 7,000 node hours on blue waters to simulate a 1 million-year catalog. A 1 million-year catalog at this point is a good length. It's long enough that we can start to learn something interesting. So last year we used about 275,000 node hours to simulate synthetic catalogs, both to get long enough catalogs that we can get statistical power to reach conclusions about events that might only occur every tens of thousands to hundreds of thousands of years, and also to do parameter sweeps. There are rate and state friction parameters in this code that we can vary, and so one of the things we're trying to do is figure out the right balance that most closely matches the observed data that we have. One of the things that's interesting about using this physics-based simulation approach, as opposed to the empirical approach for generating these lists of earthquakes, is that they actually converge pretty well. So down on the bottom, I'm showing you a hazard for California using 3 different models. The one on the left is an empirical approach version 2, which came out in 2008. The one in the center is what's generally regarded as the latest and greatest. It's version 3 of the same model. And then the one on the right was generated with RSQSim using this simulation-based approach. And so you'll notice from observation that actually USIRF3 and RSQSim agree more closely than USIRF2 and USIRF3. And if we look at a ratio plot, here white is 1. You notice that there's a lot of agreement between USIRF3 and RSQSim. And this is really interesting because these were produced using entirely different approaches, right? In one, you go off, you get paleoseismic data, you look at slip rates, and you do curve fitting. And in the second, you're doing numerical simulation. But the fact that they're converging quite well gives us a lot of confidence that we're really starting to understand seismic hazard in California. Another thing we've been able to do with these RSQSim generated catalogs is look at multifault ruptures. So sometimes, right, an earthquake will start on one fault and then it will jump to another. But getting enough data from the historic record to learn interesting things about that is difficult. With RSQSim, we can generate enough data in a long synthetic catalog that we can take a look and we see that, for example, certain combinations of faults are much more likely to rupture together, and even certain subsections on those faults are much more likely to rupture together. This is another advantage that we get from doing these kinds of simulations. So this is one thing that we can improve in order to improve our overall hazard estimates, right? We get a better list of earthquakes. So what we did then is we said, okay, what happens if we actually calculate the seismic hazard? What if we take the list of earthquakes that RSQSim produces, feed it into CyberShake, our PSHA platform, and actually produce real hazard curves? And so in the last couple of months, we used blue waters to generate what are actually the world's first fully physics-based PSHA results. I say fully physics-based because both the ERF, both the list of earthquakes, and the actual seismic hazard calculation are done using numerical simulation. There's nothing empirical about this. And so these are 2 results. You might notice, even if you aren't a seismic expert, that they have some kind of funny looking bumps on them, which we did too. So we're currently trying to understand, okay, where are those bumps coming from? We think we need longer catalogs. We need some more variability. And we also need to make a few changes to the rupture velocity speed on the fault surface. Currently, it's assumed to be a constant, and there are some issues with that. We're working on getting those worked out, and we're planning to do a whole regional PSHA study for Southern California later this year. The second element that we've been working on to improve our overall PSHA calculations is to improve our simulations. Is to say, okay, you've got this earthquake, you need to figure out how much ground motion it's going to cause. And so we do that by doing a wave propagation simulation. And so that's the second element that we've been working on improving, is improving the accuracy of those wave propagation simulations. We do this via what we call the HIF project, which stands for high frequency, meaning high seismic frequency. And so one of the things that we've done recently is we've done verification and validation with 3 different wave propagation codes. So these are all kind of under the SCEC umbrella, but they're produced by different software developers at different institutions. 2 of them are finite difference, 1 of them is finite element. One of them is a GPU code, 2 of them are CPU codes. One of them also is undergoing a new development. It's currently a regular mesh finite difference code, but their discontinuous mesh version is being developed for improved performance. And so we picked a common event. It's a magnitude about 5 event that occurred in Southern California in 2014. We have a lot of recordings for this, so it's a good one for validation. And so what I'm showing here is the verification results. So you can see seismograms as well as amplitude spectra for all 3 codes. And you'll notice that there are some small differences, but that especially there's a slight kind of time shift, but that fundamentally all 3 codes are producing very similar results, especially when you look at the amplitude and response spectra. And given that these codes have totally different histories, totally different development paths, give us a lot of confidence that we're doing a good job of modeling. We've also taken a look at validating our results against observed data from this earthquake. And so what you're looking at here are what are called goodness of fit plots. Basically higher values, the yellows and the whites are better. And one thing that's particularly interesting is if you look down here at the bottom, these are the results broken down by different frequencies. So you notice that on the left here, the low frequency results match really well. And as we move to higher frequencies, we notice that the goodness of fit plots become less good. And so this is telling us is we have kind of the basic stuff figured out pretty well, but a lot of the higher order effects, so things like topography or nonlinearity or some details about the attenuation model are still areas that we need to continue to work on. And so what we're able to do then is develop these improvements using these codes that are part of our HiF project, and then feed them back into CyberShake for our PSHA calculations and improve our overall estimates. A third thing I want to talk about today that we're really proud of at SCEC has actually been our undergraduate intern program and their use of blue waters. So every year since 2002, we have 20 to 25 students from around the country come to the University of Southern California and do an internship in earthquake system science. So we give them a grand challenge, which has both computer science and earth science elements. Typically the students have a background in computer science and engineering or in some kind of earth science. Some of them are pretty new in their careers, about half of them are community college students. And we give them 8 weeks and we see how much progress that they can make. We realize that a lot of these students have never had really the opportunity to learn about HPC or even know that it exists. And so since 2016, one of the things that we've done is we've included an HPC component on blue waters. So we've applied and received an education allocation, and that's been part of this internship experience for a subset of the students. And again, our goal is just to let them know that, hey, you know, this exists. You know, computational science is a thing, and it is a thing that you can do if you find it interesting. And I think it's actually gone really well. We're very proud of the results. So last year, the interns used 30,000 node hours on blue waters to generate over 1 million years worth of catalogs using RSQSim. They performed parameter sweeps to take a look at the impact of varying these parameters. And also, from these catalogs, they were able to extract the probabilities of large aftershocks. And then those events were actually fed into a loss model. So in the end, they were able to produce, like the plot over here, this is, I think by zip code, is the projected loss from one of the possible aftershocks that came from their catalog. And so I think it was neat for them to kind of see things go through the whole process. We've, as a result, a lot of the students that have come through the program are now interested in HPC. One of the students from 2016 went to the SC for undergraduates at the SCEC conference and is now looking at computational modeling in mechanical engineering. Another student came back for a second year because she loved the HPC so much. Another student is doing a senior thesis in HPC. Another student is doing a master's in HPC at USC starting this fall and is a GEM fellow. So actually he started at Los Alamos like 3 days ago looking at fault tolerance and things like that. So we're very excited about this as well. It's quite different from the other stuff we're doing, but being able to expose a new generation to HPC and let them know that this is out there is fantastic. And we really appreciate, you know, Blue Waters allowing them to have access to enough computer time that they can really do meaningful science. So where are we going from here? So we have a lot of things in mind. Of course, there's always, seems like more to do than there are people to do them. One thing we're interested in doing, as I mentioned earlier, is doing a full PSHA study using the catalogs that RSQSim produces. We're planning to do that in the Southern California area and the black box down here. The estimate for that will be about 500,000 node hours in blue waters. A second thing that we're actually queuing up to do right now, we're hoping to start in the next week or two, is to do a PSHA study in the area. So this entire orange box up here, it'll be the largest one we've ever done to date. The estimates there will be something like 1.5 million node hours in blue waters. We'll try to get through those in probably no more than 4 weeks. So these are fairly large campaigns, you know, without, you know, Without access to blue waters, it'd be very difficult to do these kinds of calculations. On the high F side, we're working to integrate new physics. So we're looking at nonlinearity, both at the source side and at the site side. We see that continues to become important as you go to higher frequencies. We have topography implemented in some but not all of the high F codes, so we're working on that. Attenuation, frequency-dependent attenuation is in there, but needs to be modified to be in closer agreement with what we observe. So we're bringing new physics into there as well. Ultimately, that will feed back into our PSHA calculations and continue to allow us to improve our overall hazard estimates for California. And finally, this year's Use IT intern class starts on Monday. So we, again, are having an HPC component, and in fact, we're going to bring in some machine learning this year. So we're excited about that as well. Have a lot of neat things going on at SCEC, and a lot of transformative earthquake system science that we've been able to do with access to the blue water system. I'd like to thank my collaborators.